For today's lesson, we will be discussing about the 6 circular functions. So we will be discussing the trigonometric functions and also the unit circle. So we will be discussing how is trigonometric functions related with the unit circle. So let's start with recalling the 6 trigonometric functions and also the unit circle. So for the 6 trigonometric functions, we have the sine, we have cosine, we have tangent, we have secant, cosecant, and cotangent. And of course, we can get those trigonometric ratios by looking at the adjacent and also the opposite side of a given triangle. And also to recall, we have the unit circle. So as you can see, this one is the unit circle. It involves angles in degrees and also in radians, and there are points in the circle. Now let's just try to understand how did we identify the points present in the unit circle. So let's say this is the unit circle that we have, and as what we know, the radius of a unit circle is 1. Now let's say the radius and the x-axis produces an angle that measures 30 degrees. So let's say this angle right here is 30 degrees. Now let's try to also form a triangle inside the given circle, and we will use the radius as the hypotenuse. So let's say we will create this right triangle right here. Now if this first angle is already 30 degrees, so that means the other angle, which is on this part right here, is 60 degrees. Now this triangle becomes a 30-60-90 triangle, which is one of the special right triangles. And 1 here, or the radius of the unit circle, becomes now the hypotenuse of our right triangle. As what we know with 30-60-90 triangles, there is a shorter leg and there is a longer leg. And of course, the length of the legs and also the hypotenuse are related with one another. Now, given that the hypotenuse is equal to 1, so the opposite of 30 degrees is our shorter leg. And recalling the 30-60-90 right triangles theorem, we can say that the shorter leg is half the length of the hypotenuse. So if the hypotenuse is 1, that means our shorter leg is 1/2. Now this other side here, this one right here, which is opposite our 60 degrees, is our longer leg. Now the longer leg is square root of 3 times our shorter leg. So if we will get the length of our longer leg, given that the shorter leg is 1/2, so that will be square root of 3 over 2. So again, we're able to identify the length of each legs as well as the hypotenuse of this given right triangle. Now, how is this one related with the unit circle? As you can see, there is now a point formed, this point right here, after we created the right triangle. Now, we can identify the coordinates of this point using the legs of our right triangle. So, this one, remember, this is square root of 3 over 2. And then the height is 1/2. So therefore, we can say that the coordinates of this point is square root of 3 over 2, 1/2. So the x-coordinate is square root of 3 over 2, or the longer leg of our right triangle, and the y-coordinate is 1/2, which is the height or the shorter leg of our right triangle. We can also do this with other angles. So let's say we have again this radius of 1, and let's say the angle formed now is 45 degrees. Now we can draw again a right triangle here, connecting the endpoint of the radius going to our x-axis. And since this is 45 degrees, of course the other angle should be 45 degrees as well. So this leads us now to the 45-45-90 triangle, or the isosceles right triangle. Now we can identify again the length of the legs given that the hypotenuse of our right triangle is 1. So if we were to recall the right triangle or the isosceles right triangle, so this one should be A, this one is A, and this one is A square root of 2. Okay, so that is how you can identify the sides. So this is the relationship that exists. So since this is an isosceles right triangle, that means the two legs should have the same measurement. Now, since our hypotenuse is 1, that means our A square root of 2 is equal to 1. Now, we want to get A, so all you have to do is just divide both sides by square root of 2. So this will be cancelled. You have A equals 1 over square root of 2. And then we have to rationalize this. So we will have A equals square root of 2 over 2. So this gives us now the length of the legs of our right triangle. So this one is square root of 2 over 2. And the other leg is also square root of 2 over 2. Since again, they are just the same or equal. Now, after forming the right triangle and getting the legs, we can now identify again the coordinates of this point right here, which is part of the unit circle. Now, since the legs, they measure square root of 2 over 2, so this signifies now our x and y coordinates. So therefore, the coordinates of this point will be square root of 2 over 2, square root of 2 over 2. So both the x and y coordinates are square root of 2 over 2. Now, you can do this for the rest of the angles and the unit circle, and you will now get the coordinates. So again, we're able to get the coordinates of the point given that the angle is 30 degrees and also given that the angle is 45 degrees. So that's how you identify the coordinates of the points in the unit circle. Now, we refer these points as the terminal points or the trigonometric points, which is denoted as P of theta equals x, y. So since they are ordered pairs or they are points, of course, we have the x and y coordinates. Okay? So again, these points right here, we call them as the terminal points or trigonometric point. Now, how are these points related with the trigonometric functions? So we can actually use those points or the coordinates of the terminal points in order for us to identify the different trigonometric ratios. So if a trigonometric point P of theta has coordinates xy, then the cosine of the theta is equal to x and sine of theta is equal to y. So let's just go back to this figure. So the theta here now is 30 degrees. The theta here is 45 degrees. Now, since we have here x and y, we can actually get the cosine of the theta and it should be equal to x, and we can also get sine of theta which is equal to y. For example, in this triangle here, the theta is 30 degrees. So we can actually get cosine of 30 degrees, which is equal to the x coordinate. So you just have to look at the point, and that is square root of 3 over 2. So we're able to identify the cosine of the given angle using the unit circle. You can also identify the sine of theta or sine of 30 degrees. So you just have to look at the y coordinate, so that will be 1/2. So you do the same thing with the other angle. So again, cosine, this time the theta is 45. So cosine of 45 degrees, so that will be the x coordinate or square root of 2 over 2. And the sine of 45 degrees is the y coordinate or still square root of 2 over 2. So you can identify the trigonometric ratios using the terminal points of each angle or each theta. Every angle in the unit circle has their corresponding terminal points. So these are just some of the terminal points for the special angles. So the special angles are, we have 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Again, you just have to look at the terminal points, identify what is x and y, and then you can actually get the cosine and sine of the given angle. Now, how about the other trigonometric ratios? So, given that the trigonometric point or terminal point is given, which is P of theta, and it has a coordinates xy, then we can solve for the rest of the trigonometric ratios using the following. So again, sine of theta, that is just equal to the y coordinate of the point. Cosine theta is the x coordinate. Tangent theta, it's y over x. And then for the cosecant theta, you just have to get the reciprocal of sine. So that will be 1 minus y. For the secant, reciprocal of the cosine theta. So that will be 1 over x. And for the cotangent theta, again, it's the reciprocal of tangent. So that will be x over y. Wherein, for the tangent and cotangent, the denominator should not be equal to 0. So you just have to identify the terminal points or the trigonometric point for each angle, and you can use this to identify now the trigonometric ratios. So let's say we have to determine the exact value of tangent 60 degrees. So to identify the exact value of tangent 60 degrees, we have to know first what is the terminal point or the trigonometric point for 60 degrees. So if we will go back to the table that I presented to you, so this is 60 degrees, the terminal point for that will be 1/2 square root of 3 over 2. So let's write here our P of theta is equal to 1/2 square root of 3 over 2. So by the way, the theta that we're using is 60 degrees. So let's write here. And as what we know, to get the tangent of theta, y over x. So y coordinate over the x coordinate. So to get tangent of 60 degrees, so you just have to divide y, which is square root of 3 over 2, by the x coordinate, which is 1/2. So you just have to simplify this, get the reciprocal of the denominator, and then multiply it to the numerator. So 1/2, we will get 2 over 1 or 2. So you can cancel this, then multiply. Therefore, we have tangent of 60 degrees, which is equal to square root of 3. So that will be the value of tangent 60 degrees. So another example, let's say we have to find the values of the 6 trigonometric functions of 210 degrees. So what we will do is, of course, to identify first the terminal point or the trigonometric point. So for 210 degrees, so you just have to look at the unit circle. If you want, you can memorize this. So you just have to identify the pattern so that you can easily memorize the terminal point. So for 210, this is 210. So the terminal point for this is negative square root of 3 over 2 and negative 1/2. Now that we have the terminal point, we can now identify the trigonometric functions. So for the sine of 210 degrees, we know sine is just equal to the y coordinate of the point. Therefore, the sine is negative 1/2. For the cosine of 210 degrees, so that will be just x. Therefore, the cosine is negative square root of 3 all over 2. Now, for the tangent, we have y over x. So that will be negative 1/2 all over negative square root of 3 over 2. So again, all you have to do is to get the numerator, get the reciprocal of the denominator, and multiply to it. So the reciprocal of this will be 2 over negative square root of 3. So you can cancel this. Then we have here now negative divided by negative is positive. So 1 over square root of 3. And then you have to rationalize this. So therefore, we have square root of 3 over 3 as the tangent of 210 degrees. Now, for the rest of the trigonometric ratios, all we have to do now is just get the reciprocal. So, for cosecant of 210 degrees, this is just 1 over y. So that will be 1 over negative 1/2. And then 1 times, get the reciprocal of this, negative 2. So therefore, cosecant of 210 degrees is negative 2. Now for the secant of 210 degrees, so it's just 1 over x. So that will be 1 over negative square root of 3 over 2. Get the reciprocal. 1 times negative 2 square root of 3. So this will be negative 2 over square root of 3. Then you have to rationalize. Equal to. So we have negative 2 times square root of 3 all over 3. So this is now the secant of our angle 210 degrees. And last, for the cotangent of 210 degrees, so this is x over y. So x is negative square root of 3 over 2. Then y is negative 1/2. So multiply the reciprocal of the denominator to the numerator. So this will be negative 2. So this will be cancelled. Negative times negative is positive. So we have over 1 there. So that means our cotangent is square root of 3. So that's it. We now have the 6 trigonometric functions of 210 degrees. And lastly, let's try to find the values of the 6 trigonometric functions of negative pi over 3 radians. So as you can see, the angle given to us is negative. So that means from the initial side, the rotation should be clockwise. So originally, pi over 3 is equal to 60 degrees. So from the initial side, we just have to move 60 degrees clockwise, doing the clockwise movement. So this will lead us now to this angle. So this angle right here, this is now the 60 degrees, the negative pi over 3. So that means our terminal points for the negative pi over 3 is equal to, we have 1/2 and negative square root of 3 over 2. So again, we'll do the same thing. We have to solve for the trigonometric ratios. Let's start with the sign. Negative pi over 3. So to get the sign, that will be equal to the y coordinate of the point. So that is equal to negative square root of 3 over 2. So this is now the sign of our given angle. For the cosine of negative pi over 3, that is equal to the x coordinate, which is 1/2. And for the tangent of negative pi over 3, so this is just y over x. So negative square root of 3 over 2 all over x, which is 1/2. So get again the reciprocal of the denominator and multiply it to our numerator. So we will have this cancel out to multiply. We have negative square root of 3 as the tangent of negative pi over 3. So we will just continue solving this and also solve for the rest of the trigonometric functions. So let's write here again the point. So we have 1/2 and negative square root of 3 over 2. Now let's solve for the cosecant of negative pi over 3. So this will be equal to 1 over y. So 1 over, then our y is negative square root of 3 over 2. So just get the reciprocal of the denominator. Then we will have negative 2 all over square root of 3. Then we have to rationalize this. So this will give us negative 2 square root of 3 all over 3. So this will be the cosecant of our angle. For the secant of negative pi over 3, so it will be 1 over x. So 1 over 1/2. So 1 times the reciprocal of 1/2, which is 2. So the secant now is equal to 2. And lastly, for our cotangent of negative pi over 3, so this is just x over y. So 1/2 all over negative square root of 3 all over 2. So this will be equal to 1/2 times the reciprocal of the denominator. So negative 2 all over square root of 3. So you can cancel 2. We will have negative 1 over square root of 3. Then rationalize. And then we'll have negative square root of 3 all over 3. So this will be now the cotangent of the given angle. So that's it for today. I hope you learned something about how we can identify the different trigonometric functions given the unit circle, and see you next time.